this module we will continue to discuss TM modes first, and then we will go to TE modes. As we discussed in the last module, TM modes actually have no HZ component. This makes our analysis slightly simple because you just have to solve for Ez, and then all the other quantities are expressed already in terms of Ez, so you can find out all the other components of the electric and magnetic fields. Okay. We wrote down a Helmholtz equation for Ez and then simplified it to a certain extent. So please refer to the previous module to find out where we have left it. So I will be actually continuing from the point where we left. Okay. So we had written down Ez as product of x and y and then substituted that, and that's where we had left. So we had introduced two constants, minus kx square and minus ky square, such that this plus h square was equal to 0, but h square itself, so if you rearrange this equation, h square is gamma square plus omega square mu epsilon. So this implies that gamma square plus omega square mu epsilon is equal to kx square plus ky square. So gamma is equal to square root of kx square plus ky square minus omega square mu epsilon. Now before continuing with our solution, let us look at whether we would actually have a solution, for what conditions for kx and ky, or whether we will not have a solution. Okay. First of all, gamma is equal to alpha plus j beta, right? If you want to have a solution, you do not want to have an alpha there. Why? Because if alpha is non-zero, that would indicate a wave which is attenuating, right? Because the electric fields are all assumed to be going as e power minus gamma z, which implies that you have e power minus alpha z as the attenuation factor and e power minus j beta z as the propagation factor. Okay. So if I somehow ensure that alpha is equal to 0, right, then this e power minus alpha z term can be removed, and then I will have a pure propagation of the waves. Well, what condition would give me alpha equal to 0? Look at this expression for gamma, right? So if omega square mu epsilon happens to be less than kx square plus ky square, we haven't in fact told you how to calculate kx and ky, we will be doing that shortly. But if for some frequency, mu and epsilon are constant, so if for some frequency omega, it so happens that omega square mu epsilon is less than the sum kx square plus ky square, then the quantity under the square root will be greater than 0 and gamma will be equal to only alpha. There is no possibility of any wave propagating as long as this omega square mu epsilon is less than kx square plus ky square. Assuming that kx square and ky square are some constants, right, which are constants. So as you gradually increase the frequency, right, so you have, let's say, omega axis, as I gradually increase the frequency until certain point, right, until a certain frequency which is known as the critical frequency or the cutoff frequency, the product here would continue to be less than kx square plus ky square, okay, and therefore gamma would be equal to alpha here. So gamma is equal to alpha. There is essentially no propagation, only attenuation of the waves. So waves just get attenuated. So try to launch a 10 Hz signal into a waveguide, that signal would not propagate for too long before getting attenuated and dying out. Okay. However, at this critical frequency, what happens is that this omega square mu epsilon just becomes equal to kx square plus ky square. You still do not get a propagation because the quantity under square root has become 0, and gamma is equal to 0 would imply alpha is equal to minus j beta. So you still have an attenuation, okay, and waves are still not propagating. But beyond this frequency, what would happen is that the product omega square mu epsilon becomes greater than kx square plus ky square. The moment this omega square mu epsilon becomes greater than kx square plus ky square, gamma will be equal to pure j beta. Why? Pure imaginary. Why? Because the quantity under the square root will become negative, and you are now looking for something like square root of minus 4, for example, right, which will have j2 as your solution. Of course, you will have plus or minus j2, indicating that you will have propagation along plus z direction as well as propagation along minus z direction. We will choose one of them because we know in which direction we are launching the waves. Okay. So for us, let's say we have chosen only the plus sign because we already have e power minus j beta z as the wave which is propagating along plus z direction. Okay. So you understand the critical frequency concept or the cutoff frequency concept, and this is one of the most interesting formulas that you will come across in waveguides. By the way, let me tell you here, waveguides will have lot of formulas, it will be very difficult for you to remember them. The easiest way to go about remembering them is to practice deriving all these equations, understand them, how these equations are derived, and then sit one day, on a piece of A4 size paper, you start writing down the formulas. Keep using that formula as long as you want in this particular course. Okay, once you understand the concept, there is nothing much to the formula. The formulas are only going to be complicated. You can always look up the formula. Okay, so don't worry, you can look up the formula. You don't have to memorize them, but you understand how these formulas are derived. Okay, so one of the first formulas we have figured out is the expression for cutoff frequency omega c. So omega c square mu epsilon must be equal to kx square plus ky square. This implies that omega c itself is equal to 1 by square root mu epsilon square root of kx square plus ky square. Okay, sometimes instead of writing this as omega c, some people like to split this in terms of 2 pi fc. Okay, if you do that, then fc will be equal to 1 by 2 pi square root mu epsilon kx square plus ky square under root. Okay, so this is an important equation that you can remember. But now look at what we have done. Kx square plus ky square is equal to omega c square mu epsilon, right? That is the critical frequency. Therefore, if I substitute for this in expression for gamma, I can actually write down gamma as, from this expression, I can write down gamma as square root of omega c square mu epsilon minus omega square mu epsilon. And I know that propagation happens only when omega is greater than omega c square. I can write this as j beta is equal to square root of omega square mu epsilon minus omega c square mu epsilon, but with a j outside, right? You remember this, omega is greater than omega c in this expression. Okay, so with this I can cancel out j on both sides and therefore obtain an expression for beta, the propagation constant, given by omega square mu epsilon minus omega c square mu epsilon under root. This is again sometimes written by factoring this omega square mu epsilon out, and then you write this as omega square root mu epsilon. Okay, 1 minus mu epsilon will cancel with each other. Omega c square can be written as 2 pi fc square or 2 pi fc whole square. Omega square can be written as 2 pi f whole square. So this becomes 1 minus fc by f whole square under root. Okay, so let me rewrite that same expression over here. Beta is omega square root mu epsilon, which should remind you of a plane wave solution, right? So for a plane wave, we just had this propagation constant as omega square root mu epsilon, but now there is a nice factor, there is an extra factor which will change the value of beta. And most critically, okay, although we haven't explored that, we will explore that, beta is now a function of frequency. This will lead to a lot of problems later, and we need to introduce what is called as dispersion and group velocity. Okay, we will do that. So it's interesting that we didn't even solve for kx and ky, but we already learned so much about this waveguide, right? So TM modes and as TE modes would be possible to propagate or propagate only when the frequency becomes greater than omega c. So in this context, sometimes this is called as the high pass nature of the waveguide. It means that if you have a frequency spectrum, okay, so for some way you have a pulse which is to be propagating inside, then if the frequency components are all lying, some frequency components lying below omega c, they would all be filtered and cancelled out. Only they would be attenuated out. Only the components which are greater than omega c will be allowed to propagate. Obviously this would induce distortion, because if you lose some frequency components, there is no way you can actually obtain a undistorted waveform from reconstructing the remaining sinusoids. Okay, something that you must have been very familiar with Fourier transform theory. Okay, now let's get back to finding the expression for electric and magnetic fields. We have seen that x of x, we had two equations, right? X double prime of x is equal to minus kx square. So let us solve this. The other one will easily follow from this. And go back to the differential notation. So this is actually d square x by d small x square, which is equal to minus kx square into x. There are too many x's involved, but please excuse the notation. This is quite standard invariable separable method of solution. Okay, how do I solve this equation? Well, this is second order differential equation and the product and the constant term is minus kx square. Therefore, the solutions for this x will be some constant a cos kx x plus some other constant b sin kx x. Similarly, I can find out y of y will be equal to some other constant c cos ky y plus another constant d sin ky y, right. So, I have these two expressions for x and y. So, the total expression for z, which will be function of x, y and z, will be given by a cos kx x, right, and b sin kx x times c cos ky y d sin ky y. I am trying out a new notation over here. Okay, I need to put a plus sign here because there are four terms: a cos kx x into d sin ky y, a cos kx x into c cos kx y. So, it's these four terms I am writing this in terms of these brackets. Okay, so this would be x of x, this would be y of y. All of these terms would be propagating as e power minus gamma z. Okay, so this is your electric field component Ez. Of course, one needs to also find out the components for Ex, you also need to find out the components for Ey. So, to do that one, let us first find out what is Ex and Ey, how do they vary with respect to Ez. Okay. We know that they would vary with respect to Ez in terms of Ex would vary as del Ez by del x, okay, it would be proportional to del Ez by del x, and Ey will be proportional to del Ez by del y. Okay. There are some constants involved there, but we don't have to really worry about those constants. All that is required is the proportionality constants, okay, I mean proportionality relations. Alright, I have Ez, I have expressions for Ex and Ey. So, if you actually do that expression substitution, Ex will be something like minus a kx sin kx x plus b kx cos kx x. Okay. The other things won't change, so I am going to just write down as it is. Whereas for Ey, what would change is Ey would have, so Ey will be proportional to, there could be some other constant over here. Okay, we can just put one more constant E0 just to indicate what is the power. So, but that's not really important at this point. Okay, form of the solutions is important. So, Ey, because it is dependent on del by del y, this term will not change, whereas in this term you will have minus kx c sin, sorry, this is ky, so this is minus ky c sin ky y plus ky into d cos ky y. Okay. Of course, this would also propagate as e power minus gamma z. Alright, we have obtained three components now. Okay. Have you obtained completely? We still don't know what is A, B, C and D. We still don't know what is Kx and Ky. How do we go about solving them? Well, here is where we need to apply the boundary conditions, right? So, what are the boundary conditions? Look at the cross section of the waveguide. Okay. Along x, I have two boundaries, x equal to 0 and x equal to a. Along y, I have two more boundaries, y equal to 0 and y equal to b, right. So, this entire top plate, right, this cross section will be having y equal to b. Now, there are two ways you can actually write down the solutions for Ex and Ey. Right? We know what to retain and what not to retain. A simple way, okay, would be to, depending on which one you would call it simple, one way would be to just substitute the values. Okay. So, Ex, if you look at, how would Ex be there at x equal to 0 boundary? Ex is the one which is directed along x direction, right. So, for this boundary at x equal to 0 as well as for this boundary at x equal to a, Ex component would be transverse, okay. Whereas, Ex components which are directed along x but found near the boundary at y equal to 0 and y equal to b would be the tangential electric fields, right. And we know that the tangential electric fields are continuous, okay. So, we know that E tangential is equal to 0, which means that the tangential continuity is guaranteed, and moreover, because there are these electric fields impinging on a conductor, the tangential electric fields must go to 0 at conductor walls as well, right. So, because this is a conductor and a dielectric interface, conductor will not allow you to have any Ex, the tangential component of Ex there. It does allow you to have a normal component, but that won't help you in boundary condition. So tangential component of the electric field must go to 0, and it must go to 0 at two boundaries, y equal to 0 as well as at y equal to b. Okay. What kind of a function between sine and cos will have a 0 at the boundaries? Okay. So if you have something at x equal to 0, that needs to go to 0, and y equal to 0 and y equal to b, if something has to go to 0, what kind of a function would go to 0? Why? The answer is a sinusoidal function, right? A function which would be sine will go to 0 at y equal to 0 as well as at y equal to b. Okay. If you don't want to follow this line of thought, all you have to do is to simply understand that Ex forms the tangential component at the boundary wall. Substitute for Ex at y equal to 0 and at y equal to b. So if you substitute for y equal to 0, since this is not changed, y equal to 0 will cause this term to be present, c, and then y equal to 0 will eliminate this term. All the other terms cannot go to 0, so which means that c is equal to 0. So cos kyy is gone from this solution. Okay. But from the boundary condition itself, you can clearly tell that the only solution that would remain here will be that of d sine kyy, because only the sine function, if you were to plot like this, only the sine function can go to 0 at two boundary points, which we have taken as y equal to 0 and y equal to b. Can I do a similar thing for Ex at x equal to 0 and x equal to a? Unfortunately, I cannot really do that one. Okay. But I need to use a different boundary condition in order to compensate for that one. There is another point that we need to mention here. Although the form of the solution that eventually remained was that of a sine kyy, okay, what this actually form allows us to find out what is ky. So what should be ky? Because you substitute d sine ky at y equal to 0 is equal to 0, right? That is all right. So what this simply implies is that ky cannot be found with this equation, but there is a second boundary condition, right? The electric field quantity at y equal to b must also go to 0. None of these will go to 0. So the only way that you will have that second boundary condition satisfied is ky b equal to 0. Now this equation has solutions which can be used to obtain kyb, assuming d is a constant that won't go to 0, right? And you don't want that one. If d is also 0, c is also 0, then the entire Ex is equal to 0. There won't be any electric field. So the solution for this equation is that ky into b must be some integral multiple of 2 pi. Okay. So this gives you what ky is. Ky must be equal to n 2 pi by b, or sometimes written as 2n pi by b. Okay. So this is ky. We have figured out what is ky from the two boundary condition. Let us try to figure out if it is possible to find what is kx. For that, let us look at Ey expression. Okay. So Ey in the waveguide wall, right? So this is my waveguide wall. Ey will be something that is directed along y. So at y equal to 0 and at y equal to b, these components would be normal, and therefore they won't be of any help to you in finding the corresponding boundary conditions. Okay. So they won't help you in that. However, Ey is actually tangential to the two boundaries at x equal to 0 and at x equal to a. So clearly one function which would fit as a function of x to 0 values on the two sides will again be a sine boundary condition. Okay. So you have a sine boundary condition here, you have a sine boundary condition here also. Okay. So these are the two sine boundary conditions for this particular waveguide mode that you will have. Okay. Because this Ey goes to 0 at the two boundaries, and this is essentially the sinusoidal solution that you are going to get. For Ey, the only possible way that you will have that solution is when you have b sine kxx. Okay. Again, this component b sine kxx can be used to obtain what is kx. When you put x equal to 0, nothing, you don't get anything, because b sine kx into 0 is equal to 0, won't give you any help. However, when b sine kx a is equal to 0, this equation has a solution, because kx will now be equal to 2m pi by a. Okay, right? So we know what is kx. Kx is 2m pi by a. We know what is ky, right? Ky is equal to 2n pi by b. Therefore, I know what is kx square plus ky square now. This is simply 2m pi whole square by a square plus 2n pi whole square by b square. I can rewrite this one by taking out 2 pi whole square as constant and then leaving behind m by a square plus n by b square. Now you might ask, what are these m and n? Well, these are the orders of solution. For example, with m is equal to 1, it means that there is one half cycle. N is equal to 1, there is one half cycle, because the same boundary condition can be obtained in a slightly different manner as well, right? So I can actually obtain a 0 here, have a maximum reach in between, reach a minimum, reach a maximum, and then actually have one more 0 in this way. So how many half cycles are there? There is one half cycle, two half cycle, three half cycle, four half cycle. So along this direction, which is m will be equal to 4. Okay. Similar things can be done for x direction also. So you can actually have two half cycle. So n will be equal to 2. Okay. So I will actually have one half cycle, another half cycle. Yeah. So I will have two half cycles. So this combination of m and n corresponds to the order of the mode. Okay. And we call, so this is the order of the mode, and since this corresponds to the Tm mode, we denote this mode, or we denote this possible solution as Tm Mn. Okay. So this is the waveguide mode designation. Alright. Okay. We of course need to find out whether m is equal to 0, n is equal to 0 solutions are possible, or whether they would have to be ruled out. So what possible values for m and n are there will come from looking at all the components of electric fields. Okay. So once we have obtained this, we can actually simplify those equations. Remember, we had written something about the cutoff frequency, right? So even without doing all this calculation, we had written something about the cutoff frequency, and cutoff frequency is Fc equals 1 by 2 pi square root mu epsilon kx square plus ky square. So go back to that expression and write this Fc equals 1 by 2 pi square root mu epsilon. Now I know what is kx square plus ky square, that is 2 pi whole square m by a square plus n by b square, right? So taking square root of this, 2 pi will be factored out, and inside I have m by a square, sorry, this is actually m square by a square, right, because m square by a square. So you actually have m square by a square, n square by b square, which can be rewritten as m by a whole square plus n by b whole square. This 2 pi actually gets cancelled. So Fc, and there is a square root up here. So Fc is this fellow, m by a square plus n by b square, okay, under root. So this is the expression for cutoff frequency. Okay. So we still have to figure out what is Ez completely. We have figured out what is Ex, the y dependence, Ey, the x dependence, okay, the z dependence is already known. For Ez, what would be the corresponding boundary condition, because I need to still decide whether a, b, c, d are all there or some of them are 0. So in this case it might seem that c is 0 already and a is 0 already, but that cannot be true because there is c here also, right? So we need to just figure out which one is 0 and which one is not 0. To do that one, Ez boundary conditions should help us. Okay. So with Ez boundary condition, how would that look like? Go back to the picture of the cross section. Okay. In this case, maybe the cross section does not really help, so you need to write down the wave itself. You will have this scenario, right? So this is your wave equation. So you actually have two conductors here, or it seems that you have two conductors, one at x equal to 0 and one at x equal to a, and you have two bottom conductors, one at y equal to 0 and one at y equal to b. What would be the direction of the electric field Ez at these walls? Well, Ez is directed in this way, so on the wall it would be sideways directed, I mean it would be on the sideways but directed along z axis, so this would form a tangential component there. It would also form a tangential component to the left, it would also form a tangential component on the top and tangential component on the bottom. So which means that there would be a sine type of solution here and another sine type of solution in these two directions. So clearly this would rule out a cos kx x and c cos ky y, and the solutions that you are going to get will be consisting of sin kx and sin ky. So your electric field Ez, okay, because of the two boundary conditions will look like some constant E0 which we had written, okay, sine kx we have already figured out, that is nothing but m pi by ax, right? You know what is kx. Actually for this case you don't have to write ky as 2n pi by b, even an n pi would be alright. So let me cross out this 2. I did not realize this one because sine of something equal to 0 will be valid for every pi, not every 2 pi. So I have to scratch out all this 2 here. So it's quite unfortunate that I have to do that one over here. So you will actually have a 2 sitting down here because kx square plus ky square will be equal to m pi square by a square plus n pi square by b square. Okay, so I am going to remove this 2 here and simply write down this as n pi square and m pi whole square like this. Okay, again the 2 will have to be removed. Pi square would remain, and when you take out this under square root, pi would come out and pi would cancel there. But here you have fc as 1 by 2 square root mu epsilon m by a whole square plus n by b whole square. So similarly I have in this Ez condition, right, I have sin kxx and sin kyy. There are again two constants b and d, but I don't have to really worry about those constants. I can push all those constants into E0 itself. Okay, so I can push those constants into E0 itself and then just write the functional dependence. So sin of m pi by ax sin n pi by by e power minus j beta mn into z. Again I am denoting even the propagation constant by two subscripts m and n to denote the corresponding order of the mode. But what is beta mn? Beta mn is nothing but omega square root mu epsilon into 1 minus fc mn by f whole square. You might ask, why did I write down fc mn? Well, because fc itself is dependent on m and n, therefore it seems correct to include even for the cutoff frequency, which depends on the order of the mode, the corresponding subscripts. Okay, so it depends on corresponding subscripts. So given different values of m and n, the cutoff frequencies are different for the different orders, which will also make it different for the propagation constant beta. Okay, I will leave this part here and leave finding out ex and ey as an exercise for you. We have already done most of the work. Okay, you just have to find out amongst these two which one would leave. Because a cos kxx has gone, so in this case a sin will go away. You will have b kx cos kx and sin kyy. So for ex this would go away, and for this one this would also go away, right? So this is what you would essentially be left with. Okay, sin along x and cos along y. So I will not write down this, you guys can write down. There is also some proportionality constants that you need to fill in. Okay, you can look at the textbook for the formulas. There is not much of this one to gain with, the insight to gain with. Whatever we need to understand the modes, we have already done so. Okay, one final point. Electric fields are tangential on the conducting walls of the waveguide, right? So if electric fields are impinging on the waveguides in the form of a wave, they have to introduce or they have to induce a surface current or surface current density. What is the relationship between them? You remember the surface in the skin depth analysis, we had written down this surface current density or the surface current density Js, we wrote down in terms of the transverse component of magnetic field, right? We showed that Js was actually equal to transverse component of H, and if you define the normal component of N, okay, pointing from each wall. So for example, this is my waveguide walls, right? So if I point N hat along outside of the wall, at this point also outside of the wall, here also outside of the wall, and here also outside of the wall, then I can write down the surface current density Js as N cross H. Okay, N cross whatever the H that we had applied, and of course this H must be evaluated at the surface. Okay, evaluated at surface. Okay,